All right, so welcome to my series of video on statistics. Please, I want you to subscribe to this channel, comment, like, and share. Now, in this particular video, I'm going to teach on measures of variation or measures of dispersion. Now, in my series of videos on numerical measures in statistics, I said that for us to summarize statistical data, we summarize statistical data using measures of central tendency and measures of dispersion. So in the series, I have already talked about measures of central tendency. So to gain more idea, try and find a video on that. Now, in this video, I'm going to teach on measures of variation, all right? Now, when we talk about measures of variation, we simply want to know how far the individual figures are from their average. So let's say if a set of figures like 1, 2, 3, 4, and 5, if you find their mean, you are going to get 3, okay? Now I want to know on the average how far each of these figures is from this average of 3, all right? That is the measure of variation. Now, why do we need measures of variation? We need measures of variation because it gives credibility to the measure of central tendency. Think about it. If for a group of figures, if the average is, let's say, 5, and most of the figures are far from 5, it will be very difficult to have credibility in the average of 5. So once we have an average of a set of figures, the closer the set of figures to their average, the better. Because if a set of figures are very far from their average, it means that their average lacks credibility. Now, in this video, we are going to learn a couple of measures of variation. We are going to talk about the range, the variance, standard deviation, and coefficient of variation. Now, as I mentioned, when we talk about variation, the first thing we must know is that usually a set of figures will definitely exhibit variation if they are not of the same value. For instance, if I have figures like 1, 2, 3, 4, and 5, these set of figures will definitely exhibit variation from their average because these figures are not the same. All right. But if I have figures like 2, 2, 2, 2, and 2, the average will be 2, and then 2 is far from 2 by 0. 2 is far from 2 by 0 because it's not far from, like, it's the same thing. So what we are saying is that a set of figures exhibits variation if all the values are not the same. Now, this means that we have to find a measure or how we will measure this variation, okay? How we will measure this variation. Now, one of the things I want you to know is that anytime you compute a measure of variation, and that measure of variation, the figure is very large, it means that there is huge variation that exists among the set of figures. So whenever you compute a measure of variation and the answer you get is very big, it means that the individual figures are very far from their average. And whenever you compute a measure of variation and that measure of variation is very small, the figure, the score for the measure of variation is very small, what it means is that the individual figures are very close to the average. So let's note that. Now, we are going to go through a couple of measures of variation. The first one we are going to talk about, which I believe is the most simple, but it is the most ignored, is the range. Now, Range is simply the maximum value minus the minimum value. So if I have figures like 1, 2, 3, 4, and 5, the range for these figures will be the biggest value minus the smallest value. So the range will be 5 minus 1, and the answer is 4. So what we therefore realize is that range is the simplest measure of variation. However, range is sensitive to extreme values. Now, if I have figures like 1, 2, 3, 4, 5, and 1,000, which is an extreme value, the range will be 1,000 minus 999. I'm sorry. The range will be 1,000 minus 1, and the answer will be 999. Now, look at this set of figures. If you say the variation amongst them is 999, it may not make sense. Because for the first 5 figures, there is not huge variation amongst them, okay? But for the extreme value, it is causing a huge variation. So you can clearly then see that the computation of range is sensitive to extreme values, okay? It's sensitive to the extreme values. Another one is that it ignores the data distribution. How the data is distributed from the small value to the largest value, it ignores it because it just picks the highest value minus the smallest value to compute dispersion. The next one is what we call interquartile range. Interquartile range. Now, remember in video 2 of this series, I talked about how to find the third quartile and the first quartile, where I said that the third quartile is the 75th percentile and the first quartile is the 25th percentile. Now, another way to measure variation is to find the difference between the third quartile and the first quartile. And this measure is called interquartile range. Now, this measure helps overcome the outlier problem that the range itself suffers, because the figure in the third quartile and the figure in the first quartile, they are not the beginning and then the ending figures, okay? If you have watched my video on the computation of quartiles, you realize that the figure in the third quartile is not the highest figure. And then the figure in the first quartile is not the lowest figure, okay? So once there are extreme values in a set of figures, it is better to use interquartile range than the range itself, okay? So the interquartile range helps overcome the outlier problem, and it eliminates some high and low valued observations. Now, the next one, so this is an example of interquartile range, okay? So 30 is the first quartile figure, 57 is the third quartile figure. So the interquartile range will be 57 minus 30. To know how to compute first quartile and third quartile, watch video 2 of this series. Now, the next measure of dispersion we are going to discuss is the variance, or the population variance. The population variance. Now, to go over this, I would like to show you something. Now, let's assume that we have this set of figures. We have 1, 2, 3, 4, and 5, okay? These figures, their average is sigma x over n. Let me use bigger N. Their average is 1 plus 2 plus 3 plus 4 plus 5 divided by 5. So we have 15 over 5, and then the answer is 3. Now we would want to know how far each of these figures is from the average of 3. So let's start. 1 minus 3 is how far 1 is from 3. Plus 2 minus 3 is how far 2 is from 3. Plus 3 minus 3 plus 4 minus 3 plus 5 minus 3. Now, whenever we are computing the measure of variation, or whenever we are computing how far individual figures are from their average, we also want to find the average of that figure, because you can't just want to know how 1 is far from 3, how 2 is far from 3 individually. It will be difficult to interpret. So once we compute how far each of the figures is from the average, you also have to find the average of that figure so that it can make better meaning. Okay, that's why I'm finding the average. I'll divide all these things by 5. So 1 minus 3 is negative 2, 2 minus 3 is negative 1, 3 minus 3 is 0, this is 1, this is 2. So once you add everything, the numerator will give you an answer of 0 over 5. The answer is 0. Now, mathematically, what we have done is that we subtract the individual figures, we subtract the average from the individual figures, and then we sum it up, and then we divide by the number of items. So technically, this formula, or what we have done is sigma into brackets, the individual figures, which is x, minus the average, which is by x, bracket close over n. This is what we have done, okay? Now, because of this, what it means is that anytime you find the mean deviation, you are going to get 0 because the negatives and positives are going to cancel. Now, this brought about a second idea that why don't we pick the absolute and ignore negatives, all right? So when we pick the absolute and ignore negatives, you are going to have this negative 2 will be 2, this negative 1 will be 1, and then we have 0 plus 1 plus 2, because we are ignoring the negatives, all over 5. So we are going to get 6 over 5, and that is 1.2. Now, what we have done is that we have ignored negatives, or we have found the absolute of the deviations, all right? So this brings us to another formula called mean absolute deviation, which is sigma. Now we use straight lines. We don't use bracket. This straight line means that we have picked absolute. So sigma x minus x bar all over n. So this is the mean absolute deviation when you ignore the negatives and pick the absolute deviation to find the average of that, to find the mean of the absolute deviations. Now, some statisticians also believe that this measure is erroneous, because why do we have to change a negative figure to a positive figure? Okay, so some statisticians rather advise that we square it, okay? So some statisticians advise that no, let's square the deviations, okay? Instead of finding the absolute, let's square the deviation. So here, the deviations were negative 2, 1, 0, 1, and 2. So let's square them. Negative 2 squared plus negative 1 squared plus 0 squared plus 1 squared plus 2 squared, okay? Now, once you do this, anytime you square a negative figure, it becomes positive. So we have 4 plus 1 plus 0 plus 4, plus 1 plus 4, okay? Of course, all over 5, because we are finding the mean of that. So everything here divided by 5. Now, this is going to give you 10 over 5. Okay, and that is 2. all right? So if you have followed this carefully, what we have done is that we have now squared the deviations, all right? So we have squared the deviations and we have found the mean of that, all right? So this brings into mind a formula called the mean of the squared deviations, mean squared deviation. So we call this mean squared deviation, or what some of you usually call variance, all right? It's also popularly known as variance. So this is sigma x minus x bar squared all over n, okay? This is variance. Now, some statisticians believe that we have squared it, okay? Why don't we finally remove the squaring effect by finding the square root? So we have squared the deviation. So why don't we, so when we did this, we had 2, okay? And I said mean square deviation is the same as what we call variance. Now, some believe that when we have squared them to remove the negative effect, why don't we find the square root so that we standardize the figure? So then, this is sigma x minus x bar squared all over n. So if you find the square root of this, okay, it is called standard deviation. So standard deviation is technically the square root of variance, all right? So that is how we come about standard deviation. Okay, so in computing variation, so this is the measure of variation in terms of variance. So one of the ways of computing dispersion or variation around the mean, okay, around the mean specifically, is to compute the variance, all right, the variance. And I've shown you how we got the formula, all right? So it is the figures x minus the mean, which is represented by the mu letter here, divided by n. So x minus sigma x minus the mu, or the mean bracket close squared, all divided by n, all right? Another way to rewrite this formula is this way. But I usually like the first one because it makes more meaning. Now, if you want to standardize it, as I showed you in the build-up, then when you find the square root of the variance, it will standardize the answer to the same units as the original data. Remember, we have now squared the deviations of the original data. So once we find the square root, it will standardize it back, okay? And that is standard deviation. So standard deviation is simply the square root of the variance. Now, all this we have been talking about is when we are computing standard deviation and variance for entire set of figures, or what we call the population, all right? Now, if we want to compute that for a sample, this is the formula. So for a sample, the only difference between that of a sample and that of a population is that sample standard deviation is represented by S, like this. And population standard deviation is represented by this sign, epsilon, all right? So for sample, that's one difference. Another difference is that in the sample standard deviation formula, or sample variance, if I square it, because square root of standard deviation, square root of variance is standard deviation. That means that standard deviation squared is variance, all right? So another difference is that it's the same thing. X minus the mean, which is x bar squared, but now the denominator becomes n minus 1 instead of n, all right? N minus 1 instead of n. So it's the same thing as the population, So the sample variance and the sample standard deviation, they are similar to population standard deviation, just that when we are computing sample variance, we use the X figures minus the sample mean. Then we square it divided by n minus 1. Of course, the sigma is at the numerator, okay? Then, if this was population, we will use X, the figures minus the population mean squared, of course, sigma, all over n, all right? So here, the only difference is here we are using sample mean, and then the denominator now becomes sample size minus 1, all right? Sample size minus 1. So that's the only difference. So, assuming this is a set of sample data, if you compute the mean will be adding all these figures and dividing by the number. So if you add everything, I'm sure you get 30. If you divide it by the number, there are 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the average is 3. So remember the formula for sample standard deviation is sigma X I minus the sample mean squared all over n minus 1. Then the answer, you find the square root. Okay. So here, the individual figures are 4. So the first figure is 4. The sample mean, of course, is 3. So 4 minus 3 bracket close squared plus, that's why the sigma comes in, plus the second figure 7 minus 3 bracket close, we square it. So you do that for all these figures, the 4, 7, 1, 0, 5, and all that. So when you do that, you sum everything, then you divide it by the sample size, which is 10 minus 1. Okay. So the variance will be 54 divided by 9, which is 6. All right. That's the variance. So you get 6 here. And when you find the square root of 6, to get the standard deviation, the square root of 6 is 2.449. So that is how we compute the sample standard deviation. Now, why is sample standard deviation and sample means important? Now, I can pick a set of figures. Okay, so let's look at data A. Data A, I'm picking, so the figure is from 11 to 21, all right? 11 to 21. So for data A, I'm picking these figures to find their average, right? Now, on the assumption that when I pick these figures, I can replace it. So I'm picking them, but it is with replacement. It means I can pick figures like 11, 12, 13, 16, and 16. So I'm picking 2 of 16 because when I pick, I can replace. So 11, 12, 13, 16, 16, 17, 18, and 21, all right? Now, when you sum these figures, okay, when you sum these figures, you are going to get 124. So that's 11 plus 12 plus 13 plus 16 plus 16 plus 17 plus 18 plus 18 plus 21. You are going to get 124. Divided by 8, because there are 8 figures, the mean will be 15.5. Okay. Again, in data B, if I pick 14 plus 15 plus 15 plus 15 plus 16 plus 16 plus 16 plus 17, there are also 8 figures. When I divide it by 8, I'm still, I mean, if you add them, you are going to get a 124. If you divide by 8, you get 15.5. Then use the same idea to do that for C. 11 plus 11 plus 11 plus 12 plus 19 plus 20 plus 20 plus 20 You are still going to get 124. If you divide it by the 8, because there are 8 figures, the average will be 15.5. Now, what I want us to realize is that if you use the procedure for finding sample mean for this set of figures, the sample mean for the first set will be 3.338. The sample mean for the second set, you can try it on your own, you get 0.9258. When I say try it on your own, you just use the sample mean formula like what we did here. Use the sample mean formula to, and then, use the sample standard deviation formula. Okay, sorry. Use the sample standard deviation formula to find the sample standard deviations. Okay, so you can just work through and get these figures. So the sample standard deviation for the first set of figures is 3.338. For the second set of figures is 0.9258. For the third set of figures, you get 4.57. Now we learn a very important lesson here. The lesson we learn here is that even though all the figures, so even though all the 3 sets of samples, they have the same mean, all right? But they have different variations. That is why they all have the same mean, but they have different variations. So here we can confidently say that there is more consistency in data set B as in the sample gotten from set B. The reason is that it has a very small standard deviation. That means that for data set B, we can confidently rely on their average as compared to A and what? C. All right, as I said, the lesser your standard deviation, the more reliable your mean is. That means that your individual figures are not too far from the average. Okay, and even here, the drawing can even tell that. You see, they are clustered around average of 15.5 would have been here. So they are clustered around that. Now, what if, so for this situation, it's very easy to tell, all right? The reason why it's easy to tell which of them is more consistent is that they all have the same mean, but different standard deviation. Now, what if we have a situation where 3 sets of samples have different mean and different standard deviation? How are we going to know the most consistent or the most reliable one? Okay. Now, that brings us to what we call coefficient of variation. So coefficient of variation is the ratio of standard deviation to the mean expressed as a percentage. And coefficient of variation measures the variation relative to its mean. So sometimes when we have 3 sets of data and you want to know which of them is reliable, okay, in terms of their dispersion. I mean, I said the smaller dispersion, the more reliable the average. So you want to know which of the averages is reliable by computing their dispersions. Here, first of all, check whether they have the same average. If the 3 sets of data have the same average like this, you can simply use their dispersion to tell which of the averages is more reliable. But assuming the 3 sets of data didn't have the same average, okay, you can use just their dispersions to tell which of them is reliable, because if the average is huge and the dispersion is huge, maybe relatively the average is not too big for its relatively the dispersion is not too big for its average. Okay, so once we don't have the same means, it is better to compute the variation as a percentage of the mean, or the variation relative to its mean, so that we can conclude. Okay, and that formula is coefficient of variation. So the formula is standard deviation over mean times 100%. So you can do it for the population, which is population standard deviation over population mean times 100%, or you can do it for the sample, which is sample standard deviation over sample mean times 100%. All right. So if the average is 50 and the standard deviation is 5, and here the average is 100 and the standard deviation is 5, because they have different averages, you can't just base on the standard deviation and tell which of them is more reliable. All right. So with this, we will express the standard deviation as a percentage of the mean and multiply by 100. Once we do that, we can see that data on stock B is more reliable, or it has a less standard deviation, because the standard deviation relative to its mean is 5%. All right. And here for stock A, its standard deviation relative to its mean is 10%. All right. So B is better because it has a lesser standard, standard deviation relative to its mean. All right. So B is better in terms of dispersion. Okay. Now, let's end the section with the empirical rule, the Chebyshev's theorem, and then the z-score. Now, remember that a bell-shaped distribution or a normal distribution is a distribution without extreme values. So I showed you in the series of videos, I think the series, as in part 2 of this series, I showed you how to compute that or how to show that. So when a distribution is like this, we say it is left skewed, all right? When it is like this, it is right skewed. But when it is like this, we say it is bell-shaped, all right? When it's like this, we say it is bell-shaped. So a bell-shaped data usually do not have extreme values, all right? Now, there is this empirical rule that helps us to know whether a distribution is bell-shaped. Now, if a distribution is bell-shaped or if it is normally distributed, these 3 laws must happen. Number 1, approximately 68% of the values must fall within 1 standard deviation of the mean. Number 2, approximately 95% of the values must fall within 2 standard deviations of the mean. Number 3, approximately almost 100% of the values must fall within 3 standard deviations of the mean. All right. Now, how do we illustrate that? Now, let's say we have figures like 1, 2, 3, 4, and 5. Their mean is 15/5, which is 3. All right. Now let's compute the standard deviation. It will be 1 minus 3 squared plus 2 minus 3 squared plus 3 minus 3 squared plus 4 minus 3 squared plus 5 minus 3 squared, all over n. So this is the variance. So this will be 4 plus 1 plus 0 plus 1 plus 4 all over 5. So this will be 10/5, and this is 2. So that means the standard deviation will be square root of 2. So the square root of 2 is 1.414. Okay. So if this data is normally distributed, we are saying that, remember, the mean is 3. Standard deviation is 1.4. So if this data is normally distributed, we are saying that, first of all, if you look at the empirical rule, what we